Okay, so maybe you've wondered, maybe you've never even cared, but why we're doing a unit called functions, and it's not until topic 4 that we do a lesson called functions. Maybe that seemed odd to you. I don't know whether anybody noticed, but one of the things that I found maybe is helpful in learning about functions is just I got you started doing some questions. And after kind of doing some word problems and getting used to doing that, we're not going to change that. That's still going to happen. Today's lesson is kind of a bit different than the normal lesson. Now I want to actually talk about what a function is. And if you don't know the term, we'll talk about it. If you do know it, we'll maybe refine your knowledge of a function. And then after this, we're going to go back to what we normally have been doing, which is basically we're solving word problems. Does that make sense? But I figure now is as good a time as any, after we've done a few, to talk about like what is a function. So you've probably heard the term before. A function in a math definition or even a science definition, it's a relationship between variables. Most of you today we're working in chemistry on drawing some graphs. Graphs are a great way to show a relationship between variables. And I'm fairly confident you guys did some graphing at some point in your life in grade 10. You guys want to talk about how to make graphs? Graphs are a good way of sometimes helping you solve a problem. We haven't needed to use graphs too often for solving questions in this unit, although if some of you guys have gotten to the hot dog question on the assignment, I made you draw a graph. And so that's kind of where I want to start leading into, is the idea of we're still going to use equations, we're still going to solve word problems, but sometimes a graph helps demonstrate the relationship between variables. Maybe just as an aside, sorry Andy, I know you're not in chem, but like as a relationship between pressure and volume, if pressure goes up, volume goes down. That's a relationship. Does that make sense? Well, that's a function. Technically in chemistry, we've been working with functions. We don't call them that, but anything that's an equation is a function. If I were to give you, make an equation that says that the temperature in kelvins is really equal to the temperature in degrees Celsius, if you add 273. That kind of makes sense what I just wrote there. That's a function. Anything that can be written as like an equation is a function. So that's why I kind of want to go over the terminology today. So here's some more terms you might hear then. Input and output. Input is the number that you plug into an equation, and the output is the number that you get when you're done solving. So like in chem, when I'm giving you guys equations to solve, and I give you P1 V1 equals P2 V2, sometimes I might give you multiple inputs. Like I give you a first pressure, a first volume, a second pressure. The thing you're solving for is an output. That makes sense? Okay. In math, typically we change it up, and rather than using P's and T's and V's, usually we use X and Y. You guys had some experience with that before, using X's and Y's, and hopefully you know a little bit about how we have the Cartesian coordinate plane. You guys know that term? Where this is the X-axis and this is the Y-axis. You might have seen this before. Sometimes we use F bracket X. Have you ever seen that notation before? If you ever see F bracket X, it's basically another way of denoting Y, the letter Y. What it refers to is you have a function, and the function has had X plugged into it, and this is the answer based on that X. It's a different notation. I'll show you it as we need to. You guys ever heard these words before, domain and range? Okay, well basically domain refers to all of the possible inputs you can have, and range refers to all of the possible outputs you have. So, I'm glad you guys have heard these words before. So, let me just do some other examples here. Let's try to write an equation for area of a circle as a function of its radius. Do you guys remember the formula for area? Yeah, pi r squared. So here's how we might write this in math then. The area based on a radius is equal to pi r squared. I'm going to say that one more time in case you didn't see me do that. In math, what we often do is on the left-hand side of the equation, we don't just write the letter y. Sometimes we write a and then we put something in brackets. What this means is that to find an area based on its radius, it's equal to pi r squared. I want to try another one here. I'm just going to throw another one down here. Does anybody know how to write an equation for, that's not for, that's of, for circumference of a circle based on, oh my goodness, based on radius? Do you guys know the formula for circumference, basically? What's that? Diameter? That's correct, yeah. That would be circumference is equal to pi times diameter. Here's the problem, though. I asked you to write an equation, but it has to be based on a radius. So this equation isn't quite correct. Do you guys know the formula where it's based on a radius instead? Not pi r squared. Yeah, it's actually pi times 2r, because there's two radiuses in a diameter. So sometimes we write the formula, like Brooke, you're still right. Pi d works, but the formula is 2 pi r. In math, what we would do then is we would say that the circumference based on a radius is 2 pi r. Because you gave me it based on the diameter, and maybe I don't know the diameter. Maybe I know the radius instead. However, if I wrote it like this, the circumference based on a diameter, that would have been pi times d. Does that make sense notation-wise? A lot of kids, they get confused because they wonder, why is there an extra little bracket thing next to this? All that's doing is letting you know what variable you're working with later. Let me give you another example. Sorry, Andy, I know you're not in my chem class. We had a formula in our last unit for finding a pH. You remember the formula for pH? It was like pH equals the negative log of H3O plus. In chemistry terms, that's how we'd write it. In math terms, we would have written it like this. The pH based on H3O plus would be equal to negative log of H3O plus. Does that make sense? This doesn't mean take your pH and times it by the H3O plus. It just means that the pH is based on H3O plus. That's the variable we're using. Because what happens if I don't give you H3O plus? What if I give you OH minus instead? Well, maybe you actually need to convert the OH to H and then work through that. So, first lesson then is the little thing in brackets is not actually another variable. It's just telling you what variable you're working with. Let's just try the other ones I skipped here. Write an equation for volume of a cube as a function of its side length. So, do you guys know the formula for like volume of a cube? That'll work. It's length times width times height. That's the formula for volume of a cube. Technically, if it's a cube, though, all the sides are the same as each other. So really, the length is the width is the height. So maybe a better formula is that the volume is equal to L cubed. How we're going to write this, sorry that I'm running out of room here, would be like this. Volume based on a length is equal to L cubed. That extra L that I threw in front, we don't actually times anything by it. It's just implying that the volume was based on knowing a length. What if I didn't know a length? What if I knew a height? Or what if I knew a surface area? Or what if I knew something else? Does that make sense? I actually just did the one for Celsius and Kelvin, so I think I'm going to skip that. You guys have the concept, though? Long story short, what I might do then is I might write you an equation that looks like this. F of x equals x plus 2. What this means is that we have an equation. We're going to be looking for what this thing right here equals, and it's based on an unknown x. I don't know what x is. X could be 3, it could be 4, it could be 5, it could be 27 million, it could be negative 2. Does that make sense? What we have now is an equation that relates an x that we don't know, but if we found an x, we could find the other variable. Does that make sense? All right. This came up with a few of you yesterday. You got to this point, so I just told you these definitions. When we work with data, and when we work with functions in general, there's two generic types, discrete and continuous. Discrete refers to functions where the input that you plug in, it can't be anything at all. Like, for example, typically it's based on whole numbers. Discrete means that you can have one of something, or you can have two of something, or you can have three, but you really can't have 1.3 of it, or you can't have 1.972. Like, not every single value seems to fit. So, like, for example, the number of pages in a book is discrete. There's either 5 pages or there's 6 pages. There's not 6.973 pages. Does that make sense? Or your shoe size. You either wear a size 5 or a size 6. I guess you can wear a size 5.5. But can you buy a size 5.973 shoe? It doesn't work that way. Whereas continuous is like a type of data where any number is valid. So like the length of a film is continuous. Could you have a film that is 1 hour and 3 minutes? Sure. 1 hour and 4 minutes? Sure. 1 hour and 3 minutes and 19 seconds? Sure. 1 hour, 3 minutes, 19 seconds and 47 milliseconds? Yeah, that's valid. You get the point I'm trying to make here? So that's the difference between data. Here's what makes a difference for us. When we eventually graph this data, if we're graphing data that is discrete, most of the times we start with this in our labs, we should just mark in the points. If logic dictates that the points are continuous, then we actually put a line between them. But sometimes we don't actually draw a line between our points because maybe it's just not logical to actually have like the point partway in between. Typically in science, though, we actually do fill in a line between our points. But that's because in science, can you have half of a degree? Sure. Can you have a part of a gram? Sure. But for those of you guys who did the hot dog question yesterday, can you sell half a hot dog? I guess maybe you could sell half a hot dog, but can you sell 0.97325 of a hot dog? That's not realistic. So then don't continue the line when we do a graph. That actually leads really well to my next point. Sometimes when we do functions, it actually works great that we just did a lab yesterday. When we have data, there's many different ways we can represent it. One of the most common ways we represent it is in a table. In your guys' chem lab, I made you graph pressure and volume. Well, it's the same thing as X and Y. Does that make sense? Well, whenever we have data, we can also put it on a graph. And typically on the graph, we can plot it, which I think you guys know how to do anyways. Clearly you've been doing it in my chem class. The other way we can do is we can write it as ordered pairs, where you do like first number, comma, second number. Has ever seen that before? Okay, I'll move on then. So let's do some examples now. The examples aren't going to change. Like the work that we do is not different. It's just I might throw different terminology in here once in a while. So let's try this example. You're in a parking lot. There's a flat rate of $10, and then it's $3 per hour after that. So we want to try to represent this information as a function, and then we're going to try to figure out whether it's discrete or continuous. We can still go back to our formulas. If it's going up by $3 an hour, is this a geometric or arithmetic kind of sequence? Okay, so that means we need the formula like Tn equals T1 plus n minus 1 d. That's our formula. How much will it cost you for the first hour? 13. Because it's $10 regardless, but it's still $3 an hour after that. So if you're actually in the parking lot for 1 hour, you get paid the $10, and then you still get dinged with the $3 as well. Does that make sense? So T1 is actually 13. Do we know how long you're going to be there for? No. I didn't say. Do we know what the common difference is? Yep, 3. And then last thing, do we know how much it's going to cost us for our last hour? Again, no we don't, because I don't know how long we're going to be there for. Often when I give you guys equations, I'll give you all of the variables but 1. When you write a function, we write all of the variables but 2. Does that make sense? One of them is now your x and the other one is your y. So rather than writing them with these letters, it might be more appropriate to write it like this. Y equals 13 plus x minus 1, 3. we now have an equation that we can graph, that we can plot. We just have to recognize that y is referring to how much it costs per hour. This is going to be like your cost. And this is going to be how many hours you're parked for. Another way we could write it, by the way, would be like this. F bracket x equals 13 plus x minus 1, 3. It kind of means the same thing. This just implies that the variable we're using is x. Just like right here, you see how this is t small n? We never talked about this. Anybody ever wonder why we leave the n down there? Because the n is the variable in the equation. Does that make sense? Like this t small n, the n just refers to, well, that's the unknown variable. F bracket x, the f is really like meaning you have an equation, and the equation is based on x's you don't know. To be honest, though, I'd rather go with y if that's okay, so I'm going to stick with y for now. One more thing I can do, I can expand this a little bit. So it'd be 13 plus 3x minus 3, which actually means you have 3x plus 10 when you're done. I think this is a good place for us to start, because you should have learned how to graph this last year. You remember? Remember what the 3 and the 10 refer to in this equation? 3 is the slope, and your constant term, which is 10, is the y-intercept. Do you guys recall that at all? Okay. We'll revisit it again as we start. But this is something that if you have a graphing calculator now, we can now graph. So we're going to grab a graphing calculator. Do you guys know where to type this in your graphing calculator? Should I start right at the very beginning? Okay, so turn it on, go to y equals. It's probably been a while since you've done functions in your graphing calculator. So I'm going to clear out all the old equations. And I'm going to type in 3. Do you guys know where the X button is? It's like the second button in from the corner right here. 3x plus 10. Okay, a few more things I want to show you in case you're just not comfortable using your calculator. I'm sorry if this is just totally review. One of the things you might want to change is your window size. Normally, a window size goes from -10 to 10 and -10 to 10 in the x and y direction. But that's not going to be always purposeful. In our example, what do x and y refer to? Well, one refers to how much money it's going to cost you to go parking. The other one refers to how many hours you're going to park for. Can you park for negative hours? Okay, so I might suggest that my x minimum, I should start as low as 0. Because really, I can't go lower than 0. I think 10 is still a good number to end at, though. I don't know, who's parking in a parking lot for more than 10 hours? That's a long day. Y, in our example, is now referring to how much money it's going to cost you. I don't think -10 makes a lot of sense, because you can't pay -$10 to park. At the least that would be reasonable would be 0. I don't think 10 is going to be enough, though. Because I already know that even if I just park and leave instantly, it costs me $10 before I even stay there for an hour. So I should probably make this be way higher than 10. How much higher? I don't think there's the right answer to this, but I should make it go at least higher, so I'm going to go to 50. And then, you guys know where the graph button is right here? And I'll graph it. Okay, so way down at the bottom here, for some reason someone typed in the dots down there, and you guys are trying to graph that. Oh, good question. Okay, so in the y equals up here, see how plot 1 up there is turned on? Yeah, something else we'll cover later has caused it to turn those on. So I'm going to go over there and I'm just going to unhighlight it. And now that I've unhighlighted it, now those dots should go away. If you ever want them back, which we'll get to at some point, that's actually how you turn it on and off. Any other problems I can help troubleshoot with getting a graph here? Okay, something else I want to show you then. Have you guys ever worked with the table where you go second, then you press graph and you go to table? Is that something you guys have seen before? Okay, good. Okay. Now my table is actually in a ridiculous location right now. This is 1E15, which is 1 with 15 zeros afterwards. I've actually scrolled my table so far down that it's up in like the billion range. Okay. I actually want to show you another little trick here. If you go second window, you see where it says TBL set? That's table set. Find that. My table is currently set to start at 1E15, basically a stupid large number. I don't actually want mine to be that high up. I want to start at 0. But if you wanted to make your table start at a number way in the future, that's how you could maybe do it without pressing the down button over and over and over again. Okay. And one more thing, this little triangle table means that your table is going up in groups of 1. Normally 1 is a good number to use, but let's say you wanted it to go up by 2s, for example. Now when I go to my table, you're starting at 0. You see how the x's are going up in groups of 2s? You ever seen that trick before? Okay, good. I showed you something new at least. Now, I don't know whether we need to go up in groups of 2s or not, but at least it's an option. So. I'm going to go up in groups of 1, though. 1 makes way more sense. Okay, let's move on here, because I'm taking much longer than I thought I would. But I think it's been worthwhile, though.
So then how would you write down the function?
Okay, so yeah, let's answer this question here. We're going to represent this information as a function in different methods. Here are some of the methods we could represent the data as. First method would be the equation. The equation was y equals 3x plus 10. That is a way we can represent data. Second way, we could do a table of values. So a table of values would look something like this. X and y. And then I could just go to the table of values and copy out the data that was there. I'm just going to use the first couple of points, like 0, 1, 2, 3, and 4. I think I can actually figure this out without even using my calculator, though. I think it was 10. If I don't even park at all, like if I don't even stay at all, I have to pay $10 even before I even stay for an hour, right? This, by the way, was T1. Why is it T1? Because this is 1. Some people sometimes think that this, the 10, is term 1, but that's not term 1. That's actually term nothing. Yeah. Term 1 is actually the first term where x is 1. And then it would be like 16, 19, 22. Does that make sense? So that's another way we can represent data. Typically in science, we actually start with this because that's what we record. A third way we can represent data is basically the exact same as this, only we write them as coordinate points. So we say 0 should go with 10. We say that 1 should go with 13. We say 2 goes with 16. 3 goes with 19. And 4 goes with 22. And the fourth way that we represent data is we draw a graph. Okay, my expectations of graphs are very different between chemistry and math, just so you guys know. In chemistry, I'm very picky. I want you to have axis labels. I want you to have units. I want you to have a title. I'm not looking for all of that in math. Okay. Like if we're talking about a word problem, it wouldn't be bad for you still to have labels. So like for example, this right here could be the amount of money that it's going to cost you. And this right here could be the number of hours that you have. I think I would expect that, but I don't really require a title. And normally I'd be okay with it if you just kind of plotted them by hand. Like I don't want you to go out and get actual graph paper and plot it all to scale. I want you just to kind of do it roughly where it would be. So like I might say that my graph went from 0 to, what was it, 30? And my graph went from 0 to 10. If you just write me out where it starts and where it finishes, and you draw me like approximately what the graph looked like, that's my expectation. This would have been good enough. Okay? Like don't go get grid paper, it's not worth our time. That's my expectation. You might have a different expectation with different teachers, but this is what I would want. I might ask you to plot a few points. So like for example, this point right here would have been 0 and 10. And like this point right here would be 1 and 13. But if I don't actually ask you to plot the points, then you don't have to worry about it. Does that work? No. One more thing. We should figure out whether this was discrete or continuous data. Can you park in a parking lot for a partial amount of an hour? I guess in theory you could. I imagine, though, the way that they try to screw you over in the parking lots is they always round up, I think. That makes sense. Like, even if you're there for like 3.1 hours, they're going to make you pay for 4 hours. Isn't that the way they probably do things? Like, they probably round up. They might not, though. My wife works at the hospital. She has a little swipe card because she works at the hospital. She pays to the nearest minute. So that's a little better of a deal, right? So if she's there for like 7 hours and 2 minutes because like she's late getting off of her shift, they don't actually charge her for 8 hours. They charge her for 7 point. You know what I mean? So, I would say based on this, can you stay in the parking lot for a partial amount of time? Yeah. So I would say it's continuous data. That being said, I think that they probably would, in normal circumstances, try to screw you over and make you pay by the nearest hour. But you can kind of maybe argue both, actually. You know what? You probably could make that argument, and I'd buy it as well. All right. Here's just some notes on what we just did. We just did a linear graph. In your guys' chem lab, hopefully, the Charles law graph was linear. Roughly. I don't know. Out of curiosity, is anybody's actually like a pretty straight line? The second one, yeah. Okay, well, I mean, ideally it should have been a linear graph. Alright. To start with, we're just going to work with linear graphs, nice straight line graphs. But eventually, over the course of your math lifetimes, we're going to talk about all sorts of other graphs, ones that kind of curve, ones that have like little twists inside them. My grade 12s right now are working on logarithms. Logarithmic graphs look like this. So eventually we're going to show you all sorts of different graphs and shapes and how they look. But for now we're going to stick simple straight lines. So, more slides just showing pictures. Let's do another example here. Let's do the summer tire car one. So just so you guys know, we're not doing anything different. Like the word problems will be the same. I'm adding some new terminology in maybe. I might ask you to make a graph or an equation. But like the start of how we start is not that different. So summer tires on a car have 16 millimeters of tread left on them. Every month, the amount of tread on your car goes down by 0.7 millimeters. That makes sense? So like, slowly but surely, your tires are going bald. So we'd like to now write an equation for the amount of tread as a function of the months elapsed. If you're really stuck on where to start, use the formulas I gave you. So Tn equals T1 plus n minus 1 d.
Will we ever use SN equations for a function?
No. No, we're actually only going to use the Tn equations for a function. I guess you could, but we won't. T1, how much tread is there after 1 month has elapsed? Well, when you first started, there was 16 millimeters of tread. But at the end of the first month, there would be 15.3 millimeters left. Does that make sense? So after month 1, this is 15.3. We don't know how many months you're driving the car for. I mean, ideally, you're driving the car for a long time, but we don't know. It could be 1 month, it could be 10 months. It could be 5 years. I don't know what D, though, is. What's D? Good. Negative 0.7. I'm going to put that in a bracket just to make sure that it's multiplied. And again, we don't know what Tn is, because I don't know how much tread is going to be left on the tires. So do the same thing we did last time. Actually, before I even do that, let's get rid of t's. Let's go back to x's and y's. So let's make it y equals 15.3. And then you got to like foil the negative 0.7 in. So you're going to get a negative 0.7x. We'll just change it to x. And you're going to get positive 0.7. This might be the last time we ever do it like this. What's going to happen with this 15.3 and that 0.7? It's going to combine back again to 16. So your equation is negative 0.7x plus 16. To be honest, if you can just see this equation, you could just write it. Because you guys might have learned to do that last year. This is your slope. This is your y-intercept. Now the y-intercept is not term 1 though. Term 1 is when x is 1. The y-intercept is before you even start. So before you even started driving, you had 16 millimeters of tread. And then the slope is you're going down by 0.7. Does that make sense? So if you don't want to use the Tn equation anymore, you don't have to. You can just go right to this. No. You could just start here. Like if you can see that, I'm okay with you just starting there. But I do want to show you how these two things are related, because you might think that the first stuff we did doesn't fit with what you learned in grade 10, but it actually kind of does. Like honestly, it fits with what we're doing in chemistry as well. Like it all is part of a big picture. It's one of the reasons I like teaching multiple classes, because often when I'm doing chem stuff, it fits with math. So, all right. So do we have our equation? Yeah, we have our equation. Second thing, we need a table of values for the first 5 months. So x and y, I might even be more specific. X was referring to the month, and y is referring to like the amount of tread. If you guys need to use your calculator to get the table of values, feel free, but I feel like you probably can handle this. At month 0, you still have 16. After, keyword here, after 1 month, you're down to 15.3.
Mr. Tetlock, please dial 103. Mr. Tetlock.
I should point out, that was T1, by the way, because T1 is after 1 month. Not before you start, but after you've done the month. Just keep the pattern going then. So month 2, month 3, month 4, month 5, just keep subtracting 0.7. So 14.6, 13.9, 13.2, 12.5. Does that work? By the way, in my math class, I'm not worried about details quite as much. In my physics class, I would totally ding you if you didn't have units, by the way. So make sure you don't put something down without a unit in my chemistry class. And physics if I teach you physics, I guess. But in math, I don't actually care. Usually in math, we just use x's and y's. Okay, let's go faster here. Could you guys graph this data?
Yeah.
Okay. When you graph this data, I would recommend maybe draw something like this. All I need you to do is tell me your window size. So maybe your window size went from 0 to maybe it was 20. Maybe this went from 0 to 10. And you're just going to draw me a graph, and the graph will look like this. That would be my expectation for a graph.
What do you mean by window?
Okay, so you know how like when you type it in your graphing calculator?
Yeah.
If I type in, maybe I shouldn't go too fast. Negative 0.7x plus 16. See how like this graph, maybe it's not like I'm not seeing the whole graph. You should go to window right here and play around with the window size so that you get like a good looking graph. Just like when I make you guys graph in chemistry, you should make sure that like the graph takes up most of the screen. So like, for example, as I graph this here, this goes as high as 50 in the y direction. Should it go as high as 50? Is that an economic use of my space? No. I'm going to make it go as high as 20. That makes more sense. There, now I'm getting more picture of the graph. Do you see how the graph is still going though? It hasn't like gotten down to the bottom though? I should probably make the x direction of my graph kind of go a little further as well. So I might make the x direction go to maybe 20 as well. There, that's not bad. So at this point here then, I just drew that picture. And I guess I should say that this was my window size. It was from 0 to 20, 0 to 20. The only other expectation I would have is on this axis, you should probably say like amount of tread. And this is month. That's all I require for a graph. Like literally like that. It doesn't need to be like crazy with a ruler or something. Does that work? Okay, let's keep answering some more questions then. We graphed this data. Do you guys know what the y-intercept and the slope were?
Yeah.
The y-intercept was 16, the slope was negative 0.7. Continuous or discrete? I'd say continuous. Right. Do you have to measure the tread on your tires every month? Or could you have measured the tread on the tires partway through the month? Okay, so then continuous makes more sense. Okay. I don't know why I didn't ask this question, but I feel like I should have. A really great follow-up question would have been, when will the tires run out of tread? Graphically, do you guys know where that would be on this graph? Right here? Okay, good. You guys know the word. The x-intercept would be when the tires run out of tread. You guys know that terminology?
Yeah.
Okay. I might ask you to solve that. Let's just make up a new question because it came to my mind here. If I asked you, when will the tires run out of tread? Do you guys know how to solve for that? This was your equation right here, right? The x-intercept occurs when y is 0. So I think you just said it. What you do is you put a 0 for y, and now we solve for x. So what we have to do is we have to subtract 16 from both sides. So what you get is negative 16 will equal negative 0.7x. And then if you divide by negative 0.7x and divide by negative 0.7, that'll get you the x value when there's no tread left. There's a really great argument for why this is continuous data. You don't run out of tread exactly at the end of a month, right? You run out of tread partway through a month. So you run out of tread apparently after 22.86 months is when you run out. Maybe your tire will pop before then, I'm guessing. Sorry, this is taking longer than I was thinking, but I think this is worth our investment right now. So, does that make sense? Okay, I want to show you some other calculator tricks, just in case you've never seen them before. You guys ever seen second calculate? You ever been shown how to use some of those things up here? Value, 0, min, and max. And have you guys done intersect before? Okay. Here's a trick I want to show you then. I'm going to go to my window. I want to make the window just be a little bit longer, because you know how I made this go up to 20? But the actual running out was at 22.86. I just want to make the window just a bit bigger, so I'm going to go to 25 in the x direction, just to make sure that the line actually comes all the way down to the bottom right there. Here's a couple of tricks you can play then. If you go second, calculate. Value is the very first one. It's going to take you back to your graph, and it's going to ask you, what x would you like to know about? So for example, let's say I want to prove my work is correct. I might type in 22.86. I'm going to hope that it tells me then that y is equal to 0, because it should have run out. And I mean, is it exactly 0? Well, I didn't actually use the exact number, right? Does that make sense? You guys ever seen that trick as to how to use value? Okay, so you haven't seen that trick before then? Okay. Second, calculate. It's going to take you to a list of things that your calculator can do for you. It's the very first one. It's the value. And then basically the calculator is asking you, what x would you like to know about? So I said, well, I'd like to confirm that 22.86 is when the graph is at 0.
I got error. Yeah, mine's just error.
Okay. Okay, so the reason why your guys didn't work here is that your window only goes as high as 10. And you're asking your calculator to find a number that's 22.86, but your graph is not big enough to handle that. That makes sense? So that's where the error came in. So make sure that goes at least, it's actually x that needs to go up to 25. That makes sense? Okay, I want to show you one more trick here. I only have one more example left, right? 2 more examples. Never mind, I'll save that trick for another day. Let's do another example. Try another one. You guys are good stuff? Sorry, this is just taking longer than I thought, but I'm being very thorough today. So let's try this one. Rain barrel gathers 35 centimeters after 2 weeks and 77 after 5 weeks. Does anybody know how we're going to solve this question? Just looking at the data I was given. System of equations. Well done. If you guys can pick up that's the skill you need, that's going to save you a lot of time because you were given information here and here, and you were given more information here and here, but you were given the same information like a second time. Does that make sense? So before we even do anything, we should do our system of equations. So this is really referring to like the term when n is 2, and this is again another term when n is 5. Does that make sense? So I'm going to write out my equation a couple of times again here. It was what? Tn equals T1 plus n minus 1d. So it's 35 after 2 weeks. And it was 77 after 5 weeks. They're already in a prime position for elimination. So I need 35 minus 77. So negative 42. T1 is going to disappear. 2 minus 1 is just 1d. May as well just call this 1, right? 5 minus 1 is 4d. And then 1 minus 4 would give you negative 3d. Does that make sense? Did I lose you guys there, or are you guys okay? Okay, so then divide by negative 3, divide by negative 3, d is 18, 16? 14? That's close. Mental math. And while you're at it, you should probably also solve for the other variable. So I would go back and say 35 equals T1 plus 1, because it was really 2 minus 1 for 1. But then I'll plug in a 14 right here. So then I'm minusing 14 from both sides. So T1 looks like it's 21. So there's my system of equations. I found my two variables. You guys kind of see how the big picture is kind of coming together a little bit here? I had to teach you all the mathematical skills in the algebra unit. And then now we're still using those skills, but rather than x's and y's, we use different letters sometimes. So, okay, let's go back up and answer some questions then. Determine the amount of water in the rain barrel after the first week. We just found that, 21, right? 21 centimeters, I guess. And then how much increase in water was there per week? Yeah. Really, we answered two questions at once, just by doing the system of equations. Okay, now I'd like to figure out how much water was in the rain barrel when the barrel was originally placed outside. It is 7. Why?
That's 21 minus 1 week.
Yeah. After the first week, it was 21. So therefore, like before we even started, this is a fancy way of me asking you, what was the y-intercept? Okay. So apparently when the person put the barrel of water outside, there was actually a little bit of water in there to start. Right? Like at time 0, if I worked backwards and I used like a table of values, I may as well do that. After month 1, 2, 3, 4, 5, second month was 35. Fifth month was 77. Does that make sense? This is a month. This is, I don't know, rain, I guess. Month 1 we determined was 21. Thank you. Week 1 was 21. I don't know why the person would do this, but like in theory, when they brought the rain barrel out at the beginning of week 0, apparently there would have been 7, because that's like subtracting 14 backwards. So I just want to make sure this is clear. This is your y-intercept. This is T1. And there is a difference between the two. Does that make sense? You can probably keep the table going too, right? So 35 plus 14, 49 plus 14, 63. I believe this was the next question on the test, right? Or on the string of things. So I think I've said this before to some of you guys. I know it looks intimidating because there's parts A through G sometimes, but sometimes some of those parts are actually not all that hard to solve. Or when you solve part A, it helps you find the answer to part B as well. So there was another question though, right? We want to write an equation for the amount of the water in the barrel as a function of the weeks elapsed. We can probably do that now. Y equals, we were going up by 14 every week. What was the y-intercept though? 7 only. Don't use 21 because it originally started apparently with 7 in the barrel. Can I skip the graph? You guys probably can handle the graph. Okay, and then it's probably again continuous because you can have partial amounts of water. It doesn't have to be exactly on the day or something. So. Right, let me do one more and then we can call it a day. Alright, so on this particular one here, there's a volunteer organization. Their first year they had 18 volunteers. I think I should be more specific here. I should really use the word after. After their first year they had 18 volunteers. And then after 8 years they're up to 50 volunteers. So clearly more people are coming to help out with whatever this organization is. Our goal is to figure out the increase in volunteers per year. So we're kind of back to using those first formulas again. Tn equals T1 plus n minus 1 d. What do I know? Yeah, after 1 year, we had 18. I also know that I have like a couple of points that go together. After 8 years, we had 50. Those two things kind of have to go together as a pair. But I should be able to find D. Minus 18, that'll give you what, a 32 equals 7D, divide by 7, divide by 7. What? Okay, so there's a good learning moment here. You can't actually have half a volunteer, right? So what must have happened here is we seem to be averaging about 4.5 volunteers more per year, right? But like between the first year and the second year, there must have been actually like 3 more volunteers. And the next time there was 6, and then the next year there was 3 again, and there was 5, then there was 4. Does that make sense? So, I mean, in terms of answering this question, it looks like the average amount up per year is about 4.5 volunteers. Not everything has to rely on whole numbers. I mean, normally I'll give you an equation and we'll make it whole numbers, but it doesn't have to. Does that make sense? So we should probably say that the average number of new volunteers is 4.5714. So I'm guessing some years they go up by 4, some years they go up by 5, some years they go up by 4, some by 5. Maybe 1 year they go up by 3, another year they go up by 6. Does that make sense? Which I think kind of comes back to talking about continuous or discrete. Even though we're going to use decimal numbers, this probably should be discrete data, right? Because you can't actually have half a person. So even though we're going to use decimal numbers when we write some of these things out here, that's not really appropriate. So the increase in volunteers per year we just found. Let's write an equation for the number of volunteers as a function of the year. This would be y equals, we're going up by 4 point, why don't we just make it 4.57? We're going up by 4.57 volunteers per year. How many would they have started at? Because remember, this was like after the first year they had 18 volunteers. How many would have they had kind of before?
Oh,
If we work
so
backwards.
18 minus and then subtract
Does that make sense? Like 13.43? Yeah. So one of the problems with work using discrete data in real life scenarios here is that did they actually start with 13.43 people? No, right? They probably started with either 13 or 14, and this is just kind of like the average number that makes it work. Does that make sense? So there's another way of interpreting it as well. Sometimes companies, they'll count people based on how many hours they work. So maybe they actually had 13 full-time employees and one person who was a half-time employee. Well, that is sometimes a way that you'd kind of make the numbers fit. I think you guys get the point. We now have the y-intercept, we now have the slope, and I think I've made my point. Right. So even though you get decimal numbers, like write down the decimal numbers, but technically this should be discrete data. Like we should probably be considering it to be rounded to the nearest number when we're looking for it. Okay, any questions? Okay, honestly, I didn't really add too much there. Hopefully I showed you a few new skills though, or at least I reminded you of some ones we did in the past. So. Okay, you guys have half an hour left. Sorry it was a lot longer than I was planning, but tomorrow's Flex Friday. Monday you're writing a quiz. So come sometime tomorrow, I'll print up your quiz, and that way you know what the questions are about. And make sure you finish that assignment by tomorrow so I can mark it over the weekend.